Okay, so in this video we're going to look at some past exam style questions on projectiles. So we've got a diagram showing the path of the ball thrown from X to Y. We're going to be ignoring air resistance, which graph shows the vertical component of the ball's velocity against time. Okay, so I'm going to use SUVAT to do this. So first of all, let's define my positive directions, upward and to the right. And then we're going to express the final speed, or the speed at any point, in terms of the initial velocity and the vertical acceleration, which is 9.81 downwards. So you can see the velocity graph should be have a y-intercept and have a constant negative gradient of 9.81. So that's got to be option B. So the diagram shows the path of the ball thrown to X to Y, ignoring air resistance, which graph shows the distance travelled by the ball along its path against time. Okay, so we've got distance versus time graph, so the gradient is going to be the speed of the ball. So I'm going to think about this one in terms of conservation of energy. So while it's going upward, or its height is increasing, the speed must decrease because essentially we must be transferring kinetic energy into gravitational potential energy. So that we'd see the gradient decreasing as speed decreases. So that eliminates B and C straight away because they either show the gradient is constant or the gradient increasing during the first phase. Then what we're expecting to see is on the way back down, we're starting to transfer GPE back into kinetic energy. So we're expecting to see the speed increasing, so the gradient should now increase, which gives us option D. Okay, so a train is initially standing in a station and it accelerates uniformly. It reaches the signal 25 seconds after leaving the station, and by then is moving at 16 meters per second. Assuming its acceleration does not change, what is the time taken for the train to travel the next 1,000 meters? So the first thing I'm going to do is figure out what the acceleration is, using the fact that we know it starts from rest and it gets to 16 meters per second in 25 seconds. And then what I'm going to do is figure out what its final speed would be after it travels another 1,000 meters. So that's our final speed. And then what we can do is we can get to 36 seconds by then putting that final speed in to solve the time. Okay. So the diagram shows a ball that's thrown against a wall from a horizontal distance of 3.6. The ball hits the wall horizontally at a height of 1.8 and a speed of 6 meters per second. The ball rebounds horizontally at 4 meters per second. What is the horizontal distance from the wall the ball first hits the ground? So what I'm going to do is first of all figure out the time it takes to hit the ground. Now we know the vertical component of velocity when it leaves the wall is 0 because it's travelling horizontally. So we can use that and the fact we know the acceleration is 9.81 to solve how long until it hits the ground. And then from that point, all we need to do is multiply that by 4 meters per second, and that gives us the horizontal distance when it hits the ground. Okay. So a person throws the ball vertically upwards. It rises to a maximum height where it's momentarily at rest and then falls back down. Which of the following gives the acceleration of the ball at various stages in its motion? Take vertically upwards as positive and neglect air resistance. Okay, so while a ball is in the air, its acceleration is going to be minus 9.81 if we're ignoring air resistance. So we can just select option B. As long as it's not in contact with the ground and as long as there's no air resistance, we know the only force is the weight force, therefore its acceleration is minus 9.81. So two markers M1 and M2 are set up a vertical distance h apart. The steel ball is released at time equals 0 from a point x above M1. The ball reaches M1 at a time t1. It reaches M2 at time t2. The acceleration of the ball is constant, which gives an expression for the acceleration of the ball. So what I'm going to do is I'm going to look in the vertical direction and use the fact it starts from rest. And we know the acceleration is the same in both, so the a's in both expressions will be the same. So to go down a distance of x, we know is going to take a time t1. And then to go down a distance of x plus h, we get the expression for t2. And then all we have to do is I've done the x plus h expression, subtract the x expression, and we end up with an expression for h, which we can rearrange to solve for a, which we can clearly see is option D. Okay, so our racing driver enters the home straight at 50 meters per second. He then accelerates uniformly until he passes the finish line 432 meters away. At this time, he is moving at 70 meters per second. Which statement is correct? So we've got some expressions for acceleration and the time taken. So let's have a look. So first of all, I'm going to calculate what the acceleration is, since we've got a statement about that. And so using v squared equals u squared plus 2as, we can find the acceleration is 2.7. So a is not correct. But then using that, we can figure out how long it would take to reach 50 meters per second if we start, 70 meters per second if we start at 50. So we can then find the time, which we can see is option C is the correct one. Okay, so the diagram shows the model of an arm. A force is applied by the bicep muscle that can hold the arm in equilibrium while it supports a load. Okay, which statement is correct when the arm is in equilibrium in the position shown? So the force at the pivot is 0. No, that's not going to be the case. There'll be there's been upward force at the pivot. There has to be, otherwise it couldn't be in equilibrium. The force from the biceps is bigger when the load is moved nearer to the pivot. No, so if the load is moved nearer to the pivot, the moment of its weight force gets smaller, so the force of the bicep would get smaller. The force from the biceps is equal to W1 plus W2. Again, no. First of all, the force is at an angle, so if it was the only force, it would have to be greater than W1 and W2, and there'll also be an upward force at the pivot too. And the resultant force on the biceps is 0. Yes, it will be, because it's going to have two forces acting on it. It's going to have the force at the top, the force at the bottom, and if it's going to be in equilibrium, those two forces must cancel each other out. Okay, so we've got a car that's stopped by varying the braking force. The braking force is increased to a maximum and then reduced at the same rate to 0 just as stopping occurs. In this way, a passenger in the car is subjected to the least possible jerk. The acceleration of the car during the 10 seconds is shown by the graph. So we've got a linear increase in magnitude of acceleration, and we've got a linear decrease as well. So what is meant by the term acceleration? Well, it's the rate of change of velocity. That's what acceleration is. Okay, so then on the axes of the diagram, sketch a graph to show how the velocity will change during the 10 seconds braking time. The car starts with a velocity of 20 meters per second. So let's go back to the acceleration versus time graph. So remember, acceleration is the gradient of a velocity time graph. So initially the gradient is becoming increasingly negative, and then at 5 seconds-ish it starts getting decreasingly negative. So let's put that in. This is what I reckon it looks like. So we're getting a maximum deceleration around about 5 seconds, and then at either side of it we've got the increasing and then decreasing gradient. So which feature of this graph gives the displacement? Well, it's the area between the graph and the x-axis, commonly referred to as the area under the graph. So that's what we would look at to get displacement. So estimate the total distance traveled while braking, showing your reasoning. So we could either use the area under the velocity time graph, which we can estimate, or the way I'm going to do it is actually figure out what the average acceleration is. So I reckon the average acceleration is about -2 because of the triangular type shape of the graph. And then using that and a Suvat equation, we should be able to figure out how far it travelled, and it's about 100 meters. So on the axes, sketch a displacement versus time graph for the car for 10 seconds braking time. So in the graph, the velocity time graph, remember the velocity was decreasing the whole time. So on this graph, we should see the gradient decreasing the whole time. But because it was traveling faster initially, it should cover most of the displacement actually in the earlier sections of the time, because it's traveling relatively slowly towards the end. Okay. Suggest why this method of stopping is more comfortable for the passenger than a more usual method where a braking force is kept constant during deceleration. Okay, so if you're going to have constant deceleration, there has to be a time where you go from zero acceleration to the constant value. So there's a very big change in the acceleration, and that's what jerks the passenger around. And then if you go from that constant value to zero, again, that's going to jerk the passenger at the end of the process. But by having deceleration slowly increase then decrease, there's no sudden change in deceleration, so the passenger experiences less jerking around. Okay. So figure 1.1 shows the velocity time graph for a bus travelling on a straight road between two bus stops. It's divided into four parts: constant acceleration, increase in velocity but decreasing acceleration, decrease in velocity, and then a constant deceleration to rest. Okay, you can see that in the graph. Calculate the distance travelled during the first 8 seconds. So we're going to need to use the area under the graph up to 8 seconds, which is represented by this triangle I've shown here. We figure out the area of the triangle by doing half base times height, gives us about 64 meters. The last 7 seconds, again, we can repeat this process, so it's constant deceleration, so that's going to be a triangle shape. And then again, we can get the half base times height gives us 35. For the total distance travelled, what we're going to do is we need to figure out the rest of the area under the graph. So I'm going to do this by counting the squares. So one square is 12.5 meters by multiplying the x and the y scales. And then I counted the area that we haven't already calculated the area of, so all these other sections, and I got it around 28 squares, sort of combining two halves to make it all square. So I reckon that's about 350 meters, giving us a total distance of around 450 meters. Okay, so what we're going to do is sketch the distance versus time graph for the bus. So we've got the velocity time graph, so we can use that to sketch the gradient of this. So initially the velocity is increasing, so we are going to have an increasing gradient, and then finally the velocity is decreasing, so we've got a decreasing gradient. And I used some plotted points, so after 8 seconds we knew it had travelled 64 meters, so I essentially made sure it went through a few key points at the different times. But this is our right general shape. Okay, so we want the acceleration versus time graph for the bus. So we can see acceleration is constant, acceleration is decreasing, acceleration is increasing negative, and then constantly negative. But okay. So I've got a graph that looks something like this. So I reckon we've got constant acceleration, we've got decreasing acceleration, we've got negative acceleration, and then we've got constant deceleration there shown by the graph. For a group of 10 students, each with a stopwatch and a 50-meter tape measure, write an instruction sheet for them to enable them to carry out an exercise to obtain the distance time graph for such a journey. So what we're going to do is we're going to disperse the students at equal intervals along the journey. So we're going to put them all 50 meters apart, and they're all going to need a stopwatch. So the total journey was about 450 meters. So we'll have one at 50, 100, 150, etc. And once we've done that, we're going to have a starting pistol so that everyone starts their stopwatch at the same time, and they each stop the stopwatch when the bus passes, and they're all going to use the front of the bus passing them as the point to stop the stopwatch to be consistent. And then with that, you would be able to plot your distance versus time graph.